Hi everyone. In today's lecture, we wanted to show you some simple ways of solving these circuits that we have been seeing over the last few days. Specifically, we have been using KVL, KCL as part of mesh analysis, nodal analysis to solve some very simple electrical networks. I thought in today's class I will start off with some maybe a couple of very simple techniques that will help you get practice, and then we will go through one practice problem to see how to solve it using superposition, because that is the latest technique that we have learnt. So, we will first look at the two techniques that will keep appearing again and again when you solve these types of electrical networks. We will solve them longhand in long form and then learn to use it in some applied problem. So, the first one is what happens when, let us say, you have a voltage and two resistors. So, I will draw it in this form. So, let us say I am now going to start with numbers and we will abstract it out next. So, let us say I had a 1 volt voltage source, and let us say I had a 2 kilo ohm resistor and maybe another 2 kilo ohm resistor. Let us make it the easiest possible. Now, I want to find out for this network what the voltage across the bottom 2 kilo ohm resistor is. Maybe I will just call it some unknown voltage Vx. Well, we know how to solve this. It is actually fairly simple. You have a single mesh. I will call the current through that I, and we can say that this current I is nothing but the voltage going through the loop, right, which is 1 volt, the voltage increase, over the sum of these two resistors. So, in other words, if you were to, let me maybe take one step back and even write out the mesh starting from here and ending back at the same point going clockwise. So, I have a voltage increase of 1 volt, so plus 1 volt. I have a voltage drop of 2 kilo ohms times I minus 2 kilo ohms times I, and again a second voltage drop minus 2 kilo ohms times I, and I come back to the same point. So, KVL around the loop tells me that the potential difference is 0 around the loop. So, this tells me that the current I is nothing but 1 volt over 4 kilo ohm, which is 0.25 milliamperes. What is the value of Vx? Well, Vx is simply 2 kilo ohms times I in this polarity. So, is simply 2 kilo ohms times I. So, this is 2 kilo ohms times 0.25 milliamperes. So, this is nothing but half a volt. In fact, the voltage drop across the other 2 kilo ohm resistor is also half a volt. And of course, the sum of those two voltages has to be equal to the input battery voltage. But now imagine I decided to change this to some other resistance value. How would you find out? So, we need a more systematic way of doing this. So, what I am going to do, I am going to abstract it out. So, I am going to say that I have a voltage source V and I have two resistors. R1 and R2, and I want to find the voltage across one of these. So, let us say I will call this as the voltage across R2, and I want to find out what Vx is. We will follow the same procedure. We will start from here, go around the loop and come back clockwise, and let us say that this current is I. I think you can see where we are going with this. So, we will say that V is the input voltage, maybe I will give it a name so that we do not get confused. So, I will call this V1. So, the input voltage V1 over R1 plus R2. What did we have previously? it was current was 1 volt over 2 kilo ohms plus 2 kilo ohms. What is Vx? Vx is simply R2 times I. So, Vx is simply R2 by R1 plus R2 times V1. It is simply R2 times I. What is the value of Vy if I were to call this as Vy? What is the value of Vy? Vy is nothing but R1 times I. So, Vy is nothing but R1 by R1 plus R2 times V1. What is V1? V1 has to be equal to Vy plus Vx. Clearly, the sum of these two voltages is nothing but R2 by R1 plus R2 plus R1 by R1 plus R2, which is R1 plus R2 over R1 plus R2, which is just 1. So, the sum of Vx plus Vy is simply equal to V1. So, what this tells you is that there seems to be some relationship between the input voltage applied and the voltage across some resistor in this pair of resistors. The voltage across any particular resistor seems to be the value of that resistor over the sum of the resistors. In fact, you can now extend this. So, this is a very useful thing to know, because you can quickly write down voltages and in networks. So, for example, I now give you this network. I tell you that there are 3 resistors, and I tell you that input voltage is V1, and I tell you that the resistance values are R1, R2 and R3, and I want to find out the voltage across R2. Well, I can tell you that this voltage has to be equal to R2 times the current, and the current through this is nothing but this potential difference V1 over the sum of all these resistors, because remember, resistors in series add up. We have seen this before. So, the total resistance across V1 is R1 plus R2 plus R3. The current drawn from V1 is V1 by R1 plus R2 plus R3. So, the current through the loop is R1 V1 by R1 plus R2 plus R3. The voltage across R2 is nothing but R2 by R1 plus R2 plus R3 times V1. So, I am guessing that you can see the pattern here. If you have many resistors in series placed across the voltage source, the voltage across any one of them is the value of that resistor, R2 in this case, over the sum of all the resistors, including that particular resistor, times the voltage across all of them. Now, you should imagine that I can extend this out to a current source as well, because this does not have to be only for a voltage source. I should imagine, in fact, you will see this happening again and again. Any particular property that you see with a voltage source, you should automatically imagine that there exists some similar or analogous property with current sources. For example, I take a current source and I have a resistor. Now, of course, the voltage, if I take a current source I1 and a resistance R1, the voltage across the resistance is simply I1 times R1, because I know this current has to flow through R1. Now, the situation with a current source is slightly different. So, a similar property exists if you put another resistance in parallel, because remember, just like the sum of the voltage drop across R1, R2, R3 is equal to the input voltage V1, you can say that there needs to exist a similar property for currents, except remember that currents distribute across nodes. So, remember, you apply KCL, the sum of currents entering the node is equal to sum of the currents leaving the node. So, you should imagine that a similar property exists if you were to take resistors in parallel, because now if I thought of this current as I1, this current as I2, clearly the input current I will call the input current as I, the current I has to be equal to I1 plus I2 if you were to apply KCL here. And the second thing you can say is that because R1 and R2 are in parallel, they have the same voltage Vx across them. What is that voltage Vx? Vx simply is either I1 R1 or I2 R2, they are both equal by definition. Why do I say they are equal by definition? Very simply, if you start from this, you get a potential increase I1 R1, you get a potential drop I2 R2, you come back down to the same node. So clearly the potential drop across R1 has to be equal to the potential drop across R2. So in other words, I1 R1 has to be equal to I2 R2. I now have actually two equations, so I can solve for I1 and I2. Let us say that I am interested in the current through R1, let us say I am interested in I1. So I want to solve for I1, I have two equations, I1 R1 is I2 R2, and of course the second equation is that I1 plus I2 is I. This equation tells me that I2 is nothing but R1 by R2 times I1. All I have to do is take this and put it back here. So this tells me that I1 plus R1 by R2 times I1 is I, or so R2 plus R1 times I1 over R2 is I. In other words, I1, the current through R1, is equal to R2 by R1 plus R2 times I. Now this is interesting. This is telling you that the current through resistor R1 in some way depends on both the resistors R1 and R2 through the denominator, but you can see that in the numerator it depends on R2, and this is a common observation. Basically, if you have two resistors, one of them being, let us say, much larger than the other, for example, let us say R2 was much larger than R1, this seems to show that if, so I will write it down in fact, if R2 were much larger than R1, this seems to tell you that I2 will be much smaller than I1, and this should be obvious because the potential drop across the two resistors has to be the same. The potential drop is nothing but the product of the current and the resistance. If you have a larger resistance connected in parallel with a smaller one, you should expect that the current through the larger resistance is smaller, so that the potential drop is the same across both, and that is what this equation is also telling you. This is telling you that the current through the resistance R1 is actually R2 by R1 plus R2 times I. This is slightly different from this expression for the voltage across R2. The voltage across R2 was R2 by R1 plus R2 times V1, whereas the current through R1 for a parallel combination of resistors is R2 by R1 plus R2 times I. So if you have two resistors in parallel, the numerator on this side will actually be the other resistor. So, there are many properties such as these. There are also some properties that will help you actually simplify networks, and I just want to tell you two of them. The first one is to realize that if you have a connection like this and then you are connecting to something else, some network n, let us say, I am going to abstract out that network n, some voltage V and some resistor R. As far as the network n is concerned, this is exactly the same as having a voltage source without the resistance R. So, if I call these nodes some n1 and n2, in other words, a resistance across a voltage source really does not affect the rest of the network. Why do I say this? Very simple, the voltage across the resistance is of course V, the voltage across the network is also V. Therefore, in both cases the current through the network does not change, I will call that IN. Now, the current drawn from the voltage source changes because now I have some current IR, but as far as the network is concerned, nothing changes. This is also a very useful property. The current drawn from the voltage source in the two cases is of course different, but as far as the network is concerned, it is exactly the same. Now, you can now imagine, as I told you earlier, you can draw similar properties for current sources. So, now you can imagine I have a network n prime, I am going to connect a current source I across two nodes n3 and n4, and let us say this is some current I and some resistance R. What is the current flowing through n3? It is I. What is the current coming out of n4? It is I, and therefore, you can say that this is exactly equivalent to having this current flowing through this into this network n prime at n3 and n4 without the resistance. You have the same current I flowing into n3 and coming out of n4. As far as the network is concerned, there is no change at all. What changes between these two networks? Again, in the earlier case, the current drawn from the voltage source was different. You can now imagine that if there was a voltage drop V here, or I will call it Vn prime, you will of course have the same voltage drop Vn prime here, but in the first case you had a voltage drop Vr across the resistor, and that voltage drop, sum of those two voltage drops will now appear across the current source. But remember that we are talking about ideal voltage sources and ideal current sources here. What was the characteristic of an ideal voltage source? The characteristic, if you look at the VI characteristic of an ideal voltage source, it was parallel to the x axis. Let me call this voltage some V1. The voltage source, ideal voltage source, can actually supply any current that is required without changing its voltage, as long as the voltage applied to the network n stays the same, the state of network n will look the same. And similarly, if you take the current source I1 will have a characteristic like this. As long as that same current I1 is being fed to the terminals of n prime here, the state of n prime will remain the same. So, it turns out that this is a very useful property to solve networks.